So now we're ready to start talking about a naive approach to blocking for registers. What do we have here? We're performing a matrix-matrix multiply, C updated with A times B. We have partitioned matrices C, A, and B into small submatrices. And we are highlighting here a typical step where a small submatrix of C is being updated by multiplying the appropriate submatrices of A and B together. In order to do that multiplication, their elements need to be in the registers. So a very naive way of looking at this would be to say, well, when we get to this point in the algorithm, we move the three blocks, one from A, one from C, one from A, and one from B, into registers. We perform our computation, and then we write the block of C back out. Notice that we don't need to write the blocks of A and B, because those blocks are not being updated. So over here we have the whole algorithm. The operation that we perform is this update with three blocks, but then we need to have some triple nested loop around that in order to do all of the multiplications with the submatrices. And we happen to have chosen the order JIP, and why we do that will become clear shortly. So what do we have? We loop, we loop, we loop. We load the three blocks. We perform our computation. We store the result back off to the next iteration of the loop. So the cost of moving data around can be analyzed as follows. Let's see, what does it cost to load these three matrices? Well, the size of the first matrix is MR by NR. The size of the second matrix is MR by KR. And the size of the third matrix is KR by NR. Submatrix of C, A, and B. And we need to multiply that times the cost of moving one double around, and that's R beta RM. All right? But then we also have to store the block of C, and therefore we need to put a 2 in front of that. But that's just the cost for loading and storing in the innermost loop. We need to do that k times for this loop, and then m times for this loop, and n times for that loop. Right? Now, we can also analyze the cost of doing a matrix-matrix multiply with blocks, and then we need to say, and we do that many times because we have all of these loops. But realize we're just doing the same computations as we would if we did a regular matrix-matrix multiply. We just happen to do them in chunks. And therefore we know that the total cost of the time spent in actually multiplying is still going to be 2 times m times n times k times the time it takes to do a floating point operation. So we don't need to spend too much time analyzing that. Although in the notes you will find all of the formulas that will walk you through all of that. All right, so we have now this formula for how much computation is being performed, and we can turn that into something a little bit simpler. Sorry.
That's how memory movement, not computation.
So we now have this formula that tells us how much memory movement happens or how much time is being spent in moving data around. And we could simplify this by realizing that big M times MR is just little n. Big N times NR is just little n. And big K times KR is just little k. It's the total size of the matrix. So what kind of simplification can we get here? Well, we can write this as 2 times M times MR times N times NR times K plus, capital K, plus M times MR times K times KR times N plus K times KR times N times NR times M, quantity times beta R M. And when you write it this way, you see that this is just little m, this is just little n, and so forth. So the total time spent in moving data around is given by 2 times m times n times let's see, k divided by kr. This is little k, little kr, plus m times n times k divided by nr, plus m times n times k divided by mr times beta r m. And writing it this way is convenient because it'll make it easier for us to compare how much time we're spending in moving data around relative to the time we spent moving, actually computing. And of course now we can pull the m, n, and k out, and we get m and k times 2 over kr plus 1 over nr plus 1 over mr times beta r m. Okay, so the good news is the fact that we're blocking is going to make this a smaller number. And of course, the bigger we can pick those blocks, the smaller this number gets, and the less time we spend in moving data around, and the more time we spend doing useful computations, and that's a good thing. So that becomes part of the game now. Good enough?